You can mess with it all you want, right?
I don't know.
Does that look like it's pointed at the screen?
Yeah, but I don't think it's at a good spot.
That'll work. You think that'll work? Maybe I should go like that. Or like over here or something. Yeah, side view. There we go.
Okay, hello, how are you? Good? Okay, have a couple of things to announce. Okay, like this. So, no class next Tuesday. I need to leave. We now still that day. So, you have 1 extra hour to study for the final, for the midterm, not the final. Okay, for the exam on Thursday. What happened is that my office hours on Monday, if you have any doubt, any question, Monday is normal hours, 1, 2, 3, but I will be here all Wednesday. Send me one email if you want anything or you need any explanation, any more information, I'll be happy to, okay? So today you have a quiz for me, and I'm gonna give you another one. That one is due on Tuesday. Again, I'm not gonna be here, so please bring it to my office, put it below the door, okay? Bring it to the main office of environmental science, okay? Which, this is good, then you will know where is my office. For those of you that you're not gonna come never to my office, I know, half of the class is not coming to my class, I to my office, at least you will come to deliver the quiz. And then you know where is my office and you can come by when you have questions, okay? Remember, when I was a student, I didn't go to the office hours. I don't have to need anything, and then I realized that I didn't get good grades because I have a lot of doubts that they are easy to ask the professor. Something as simple as, I don't know what is a cofactor, but I'm going to talk about that now. Okay? So, the quiz of today, you're going to give it to me at the end of the class, and the next quiz, I'm going to give you on Tuesday. So that's the 4th. That's the last one before the midterm number 1. So if you have given to me all the quizzes, at least for quiz number 1 and number 2, you gave it to me, all of you, you already have 2 points out of 100 of the grade of the midterm number 1. If you give it to me, the one today and the one on Tuesday, you will have 4 points already. Those are really good. What else? Just one small thing to mention. I checked your quizzes from the last day, and as I expected, let's go back to enzymes and cofactors. Okay? I will be fast. Catalyst, you know, an enzyme is a protein, you know that. Now you know really well that cytochrome P450 is abbreviation of cytochrome P450 oxidoreductase. It's a protein. A cofactor is organic molecular, it's organic chemical, it's not a protein. So cytochrome P450 cannot be a cofactor. It's a protein. It's an organic chemical, a cofactor. Most of you did it right with NADPH. What else? NADH, glutathione is a cofactor, glucuronic acid is a cofactor, so here you will have done it well. But a few of you put as a cofactor cytochrome P450. Again, cytochrome P450 is not a chemical. It's the abbreviation of a cytochrome P450 oxidoreductase. That means protein. Okay? Again, oxygen is not a cofactor. Some of you put it there. Hydrogen is not a cofactor. Water is not a cofactor. Okay? When you do those reactions and I'm asking you a cofactor, that doesn't mean that it needs to be a cofactor. Any cofactor is necessary, just put known. cross it. Don't write anything. Don't fill, how to say, it's not mandatory to fill all those, okay? Because I think that somebody got the feeling, no, I need to fill, there is something here. No, you can mention no. Okay? Again, cofactor. Inorganic ion or organic molecule, organic chemicals, not proteins. I don't think I need to go with DNA, protein, description, okay? What is the difference between an organic chemical and a protein, okay? That's pretty much. It's a cofactor, it's organic molecule, okay? You, in this reaction, you tell me alcohol is the substrate, it's not a cofactor. Factor is helping. That's pretty much. Okay, no more class for today. No, now let's go to the hard part. Toxicokinetics. Honestly, I don't like this class. Toxicokinetics. Not you guys, okay? The topic. This is the most boring part. And more, how to say, everything is abstract. It's more numbers, formulas, more numbers. But toxicokinetics is the way that we put numbers to physical things or physical toxicity, okay? So I summarized the part 1 and part 2, and I eliminated most of part 2 that you don't need to know, because one, I'm canceling the class on Tuesday. I will put that announcement in Canvas, you know, the people that is not here, so they don't want to be here alone and asking, what is the rest of the people? Okay? And I summarize all toxicokinetics in one. Okay, it's a lot of terms to know, to memorize, to understand. So let's start with some definitions. Okay, what is toxicokinetics? Here is the book definition. It's the study of the modeling and mathematical description of the time course of disposition of xenobiotics in the whole organism. Okay. The friend description is we put numbers to toxicity. Okay, toxic to the behavior of the xenobiotic in the body, we put numbers. Why we need numbers? Because we need to be able to predict. Okay? We need to be able to know and to compare different compounds. If we don't put numbers and we don't do modeling, we cannot predict. Okay? So we have two models of toxicokinetics, classic models and physiologically based models. Okay, the classic models, the difference is that the classic models, they use, they are based on this, on the chemicals move through the body as if it was a box. Okay, that's a more simply way of doing a modeling. So we are not a body, we are a box. You put chemical in, chemical goes out, that's it, it's a box. You can have one or two boxes connected with tubings. That's the compartmental model, okay? That's the classic. But those ones, they don't take into account the anatomic reality or physiology, okay? Because we use the plasma is a box, the lungs another box, kidneys are another box, brain is another box. All the boxes are the same. But you know, brain is more ligated than, not really kidneys, but more than lungs, okay? And muscle tissue is different, has more, so we have more muscle tissue than kidneys. So we don't take into account that. The classic model, kidneys are the same as muscle tissue. It depends on the compartment that you make. The physiologically based models, it's more accurate to reality, okay? So those models will take into account each organ, the characteristic of each organ. So they are not boxes anymore. Okay, we take into account that the perfusion of the lung and the elimination of the lung, the metabolism of the lung is totally different to the liver. Okay? In the first one, we consider that the liver is the same as the lung. They metabolize the same, they do the same. In this case, no. Okay? So as you may think about it, those models are way more complicated. And why we have classic and physiologically based models, because before we only could do those. Technology, computer modeling allowed us to do those ones. Not the same to calculate a series of equations manually or with a calculator than to do a whole human model with all organs, a bunch of factors, a bunch of equations, okay? That's something that you cannot do manually. Okay. Again, the purpose of toxicokinetics is to quantify those ADME, remember absorption, distribution, metabolism, and excretion, okay? Just to put some numbers to this, so we can compare different compounds, different organs, okay? So the value is this, to understand everything, data collection, interpolate and extrapolate, okay? That's related to prediction, okay? And to reduce animal usage and human usage, okay? To reduce the clinical trials. ADME, you will have nightmares about that when you study for the exam, okay? We've been going through that a bunch of times. So now, again, toxicokinetics put some formulas and numbers to this, okay? This is the same, kind of more realistic. Absorption, remember that, distribution of metabolism in the body, elimination, so we can make as many boxes as we want to. And then, let's start in depth about those two models. So, most of it we're going to be talking about the compartmental, the classic model, okay? It's the basic model, it's easy to understand, and then we will end up talking about those PBPK models. PBPK stands for physiologically based pharmacokinetic models, the same as physiologically based models, okay? So, as I mentioned before, and I will keep repeating the whole class, compartmental pharmacokinetic model, the classic model, the body is different compartment, boxes, okay? Which they are interconnected by rate constants. The rate constants, as the word constant established, that they are the same always. Elimination and distribution are the same in each box. Metabolism is the same in each box. Okay, we're assuming that. And that's the more simpler model. For the PBPK model, we assume, and it's more realistic, that the metabolism of each box or each compartment is different, the elimination is different, excretion is different, distribution is different. So imagine that you have to do a model. With the classic model, you need to measure how much is going in, how much is going out. Easy. For this model, you need to measure how much is going in, how much is going out, how much is get distributed, how much gets metabolized, so a bunch of factors. Try to do statistics with that. Have you done statistics? Kind of PCA, principal component analysis, data reduction. So that's why we need computers to do these models, okay? Now, let's talk about the first, the classic model. Okay, parameters and definitions, and why do we use that? Okay, as I mentioned before, the compartmental model consists of a central compartment, a box, okay? It's representing the plasma and tissue that equilibrate with the chemical. So we have two different ways. That's easy. One compartment model and two compartment model. Which is different? That. One box or two boxes. Okay? The one compartment model is you measure how much is going in, how much is going out, and the rate is the same. Okay? In two compartment models, you have the central, that's tissue, okay? Again, as a box or compartment, you define them. It's not that the lung is always a compartment, no. It depends on your study, it depends on if you are an MD, okay? It depends on you. So a compartment can be a tissue, can be plasma, can be a cell. Okay. But again, the one compartment model only uses one. So normally one compartment model is, or plasma, or the whole body. The two-compartment model, the central is the tissue, and the peripheral normally is the plasma. Okay? It's just because I'm asking you how much of your pharmaceutical compound or your toxic compound is going, I don't know, how much are you going to accumulate in your lungs or in your kidneys? You need to take into account how much is going in, how much is going to the plasma, going on forward, and then how much gets eliminated. That's the easy way you can compare a toxic compound, okay, between them. Then you may think, why are we using those compartmentals? They are really simple and they don't reflect the reality. Again, they're good to start calculating those constants. So we can predict the plasma concentration at different doses. So we keep using this model, okay? And this is the easier and faster model for the compounds, okay? You can establish time course of chemicals in plasma and tissues, really easy, okay? You can even calculate some bioaccumulation of the compounds, and you can determine effective dose, okay? You have a pharmaceutical compound that you wanna know if it's doing something on your experimental human, say rats, okay? Not allowed to experiment with humans yet. Kind of. So what you want to know is how much of your compound is going to the plasma. It doesn't matter metabolism. Now you don't want to know that. You want to know that you don't want to kill your rat. Okay, you know how much is going in, how much get into the body, how much gets equilibrated, and how much is going out. And the effect, if the rat survives or dies. Stop. So that's why we use this one compartmental or two compartmental model. So this is the classical model. If you want to go more in detail, then you go to the PBPK models. Okay, that's way more complicated and time consuming. So one compartment model. Let's put some mathematics to work. Okay. Those toxicokinetics are kind of second degree equation, but when you do the logarithmical, it's straight line. It's only one equation, one box, one equation. Is that easy? Okay. So you are assuming that they equilibrate rapidly or they mix uniformly between blood and tissue. So everything is going there, no metabolism. Or if there is some metabolism, we don't take that into account. So there is a straight line when you plot it on time, over time, okay? So your compound, or your pharmaceutical compound, your toxic compound is going down with time in a straight line when you plot a logarithmical and a semi-logarithmical plot. Okay. This is the equation. I used to explain those ones before, but don't be too scared about the equations. You only need to know 3 of them. I'm gonna show you like 5 or 6. I will tell you later which one you need to remember. Okay. This is how we can calculate, okay, the concentration of the compound, knowing the initial one and the constant of elimination versus the time. So if you see this, what I want you to see, it's a constant, this one, okay? So this model doesn't take into account only the time, okay? Doesn't take into account any other thing. So that's valid for all the boxes, all the compartments, okay? And it's linear. Two compartment model. The difference is that when you plot it, it's not linear anymore. You have 2. Why you have 2? Because you need to take into account one box that is linear and another box that is linear. What happens when you have one line and another line? You have a curve. Okay? It means that in one box is faster the equilibrium, so your compound is incorporating or distributing one box faster than in the other. That's obvious when you have 2 boxes. Think about an aquarium. You have 2 aquariums connected with a tube. You put water in the first one, this one will be filled and to the tube, and then second will start filling. So this one is faster than this one. If you calculate how much water is coming to the first aquaria in a line, it's gonna be up, okay? Doesn't matter, we do the inverse. So it's gonna be this way, faster. This one is gonna be nothing until it's going up again, okay? Does it make sense? So when you plot both aquaria, one of them is going this way and then the other one. So that's the big difference between 1 and 2 compartment model, okay? And this is the formula. Yay, no, don't worry about that one too. This is the same as the previous one, but you added both. It's like this one, this is the constant of elimination over time. This is the same constant of elimination of one box, and the other compartment, plasma normally, okay? So the concentration will depend on both, the addition of both of them. Okay, I keep mentioning about pharmaceutical compound, toxic compound, sometimes I call them pharmaceutical or toxic compounds. So remember that toxicology and pharmacology are two parts, again, bright side, dark side. We use the same term, the same kinetics, the same. So what you are measuring is, or you are measuring your pharmaceutical compound, or you are measuring your toxic compound. The only thing is that, again, one is the dark phase, okay, the toxicology is measuring toxic effects. And the pharmacology, you are observing the good effects, okay? So we use the same, so let's call it, now we're talking about toxicokinetics, but this class we can call it pharmacokinetics, okay? Same formula, same models. So we have something called therapeutic range, okay? Normally when you inject a pharmaceutical compound, it's going this, so this is the effect area under the core. This is just some definitions that you need to remember when you see some graphs, okay? And you may say, oh, is that familiar with a toxic compound? Okay, so this is pharmacokinetic. You see the therapeutic range is when you have the effect that you want to, okay? Cmax is the maximum concentration that your compound is reaching the plasma or in the blood, and then it's going down over time. If you change this for a toxic compound, you change the names, most of those ranges. But this is the same, concentration of the toxic compound that you get exposed to. Area under the core will be your toxic effect. And then therapeutic range will be your maximum toxicity or your lethal rate or lethal range, okay? This is to show you that it's the same pharmacokinetics and toxicokinetics, that we only add the tox at the beginning and that's all. Okay, elimination. I love those formulas before and then I got tired of them and scared. Yeah.
Well, on the last slide, what was the MTC and MEC on the right?
Minimum effective concentration. I think it's maximum toxic concentration.
Okay.
Okay. The effective concentration is the minimum that you need to reach to have an effect. This is the maximum. I think maximum total toxic concentration is more than that. It's really far away from the dose that you are putting, but if you reach that, you will kill your animal or your animal, okay? This is for pharmacokinetics, okay? We face it on the other side of the mirror, okay, for toxicokinetics, okay? So this will be minimum toxic concentration, and this will be lethality, so imagine that you are far away. Okay? It's going to be different curve, but just the terms are different. So I think that it's useful for you to know what is pharmacokinetics, because most of you will go probably to medical school, and in medical school, really we care more about, they, I'm not even a doctor, an MD, I mean. So they care more about pharmaco. Okay, you will see this a lot because you need to know how much you are giving to your patients for not to kill them. It's too direct, but that's true. Okay. Okay, elimination. Next step. The elimination in those models. Okay. The whole elimination, it's including biotransformation, exhalation, and excretion. So we don't make differences in the classic model. We call it elimination. Okay. It's occurred through a first order process. I will mention what is a first order later. Okay, it's not useful now because it's gonna be more confusing than it is. Okay. So the elimination is this. If we wanted to calculate the constant of elimination of a compound, so we know how much do we have. So you measure the blood of a patient. Okay, you get blood. You know how much after given, you give a dose of, I don't know, vancomycin. Okay, IV. You know this. After 6 hours, you measure blood again. You know this concentration after 6 hours. You know the time. So now, you need to know what is the constant of elimination in this model. So we just isolate that, blah, 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 blah. You isolate that, okay. I don't know why I had this for a longer class. You are lucky this year, okay. And then you have to do anti-log, blah, 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 calculus, and you get the constant of elimination. Okay, you have, again, I don't know why I have those from the last one, but it's good for you to have it. The most important thing is that out of this equation, you can isolate the constant of elimination. You can know that, okay? And again, this is the first sentence, is the more important. Includes all kind of transformation, exhalation, and excretion, okay, in the classical model. Another thing important, volume of distribution. We mentioned that when we're talking about distribution in the ABE class, okay, absorption, distribution, and excretion. And we just mentioning what is that. Here is where we learn what is, okay. Is the constant, it's a volume that relates the total amount of your chemical in the body versus the concentration in plasma. It's not a real value, it's not a real volume, okay? The volume of distribution of paracetamol for one person, maybe 80 liters. For another one, you calculate it, you are a doctor, you calculate it for another one maybe 1. It means that that person has a problem of distribution, okay, between plasma and the tissues. It's not a real volume. I keep insisting on that, okay? It's the apparent space into which amount of chemical is distributed in the body, okay? It's a number. It's not a real value. So how you calculate that is, you know the dose that you injected and you know the initial concentration. You divide it, okay? Let me show it to you in a more abstract way. So again, it describes how a toxic compound is distributed to the whole body compared to the plasma. It looks like I'm reading the slides, but I did them so well, and I put it in my words that I don't know how to say it in some other way. So my English is really limited. So okay, this is what happens when you put a pill or a toxic compound or a pharmaceutical compound into the plasma, rarely distributed equally between plasma and the rest of the body. Normally that doesn't happen. I should say never, but again, sometimes it happens, okay? This is more normal thing. So when plasma gets distributed more in plasma and less to the rest of the body, you have a low volume of distribution. When you have low volume distribution, you have more of your compound is in plasma. Okay? What happened with this compound? It means that it's really soluble, doesn't cross the membranes, it's not apolar, so it stays in plasma. Doesn't go to the tissues. If you have high volume of distribution, it means that the compound is going faster to the tissues. It's a apolar compound crossing the membranes, so it's going out of the plasma. Okay. What else? Yeah.
How does volume distribution relate to elimination? So I had a conversation with somebody and they told me it doesn't, or something like that.
Here, it's the next slide.
Gotcha.
That's a good question. Yeah.
I'm confused on the formula. Like, how do you differentiate between dose and CO? Like, aren't they the same thing?
This is the concentration. This is what you are putting in. Dose is what you are putting in.
Right.
In your pharmaceutical or your milligrams, grams. Okay. And this is at the zero time point, the concentration in plasma.
At time 0?
At 0.
Okay.
That's how you know. Okay. So one is the dose. It's 3 milligrams per kilogram that you are injecting to myself. Okay. And then you determine this at time 0. Time 0 is just after injection. Okay. That's how you determine the volume. We're assuming that the distribution is really fast.
Okay.
It's really super fast.
Alright.
Incredibly fast. Because time 0, both of them, okay? Oh no, this is not really time 0, this is the one that you have in your injection, okay? And this is the one that gets into the plasma once it's in the body, okay? Clearance, this is fast, this is really easy. This is the rate of the chemical elimination from the body, okay? Again, the total is you can add it, all the clearance from the body. So let's talk about that later. Clearance is a combination of volume distribution with elimination, okay? Constant of elimination is how much is going out of the body, okay? It's quite similar to clearance, okay? But clearance is per unit of time. Okay, one compartment model is this is how you relate clearance to volume of distribution. Okay? Constant of elimination is always the same. Volume distribution is changing. Okay? That's how you relate